Okay, hi. So this is the second video on von Mises. So what I'd like to highlight is this is how von Mises derived his criteria, as in the yield due to the energy, distorted energy, is the U squared over 6G based on this condition. Okay, so from here he tried to apply to any other structure. Okay, so the next thing that he highlight, or von Mises' theory highlight, that the structure is safe when the energy to distort, or the distorted energy on the structure is less than the energy that's distort. Okay, there's distorted, the distortion energy up to its yield. Okay, so this is a criteria. So when that's the case, you will write this expression out where you have stress A squared minus by stress A stress B plus by stress B squared is less than stress U squared. Okay, so how this expression is derived, okay, so I'm going to show you now. So this is what we call, before I show you, this is what we call von Mises. Okay, von Mises criteria. And stress A and B are so-called, not are so-called, are our principal stress. Okay, so stress A and stress B are our what? Are our principal stress. Okay, so now how we derive this is basically, if you come back to this expression over here. Okay, so this is our expression that we have. Okay, we have this. So this is our distorted energy of our structure, right? Okay, so this is a distorted energy for structure. It has to be less than what von Mises call his criteria. Okay, so this is stress Y squared divided by 6G. Okay, so you get rid of them. So that's where you have the expression where you have stress A squared minus stress A stress B plus by stress B squared is less than stress U squared. Okay, so if you look at this expression over here, right, the parent function will take the form of x squared over a squared, right, plus by y squared over b squared is equal to 1. So if you were to expand this out, what you get is b squared x squared plus by a squared y squared is equal to a squared b squared. So if I just bring it across, a squared x squared minus by a squared b squared plus by a squared y squared is equal to 0. This in fact is an equation for, it's known as an ellipse equation. Okay, so now we can plot this in terms of stress A and stress B now. Okay, so this is, we're going to plot this on stress A. So this is our stress A. And then we have our stress B. So you guys have seen this before, okay? You get familiar with. So if this is our yield minus negative yield, A and B are our principal stresses, right? So for Tresca, we know it looks like this. Okay, so this is for Tresca. Okay, so I'm sketching out Tresca. So this is for Tresca's expression or operating limits, and we know why it looks like this. Okay, fine. So this is Tresca's. And now, okay, so this is for Tresca. So as I ask you guys to standardize, so this is Tresca. Okay, so this is maximum shear. And if you were to sketch or plot out von Mises, it will look like this. So what you see down here is you will see an ellipse. Okay. So this shaded region, right, is where von Mises, right, cover more area than Tresca. Okay, so this orange or this red, okay, including Tresca, this is von Mises. So von Mises is more less conservative. Okay, so less conservative means it push it closer to its yield. That's what it's trying to do. Okay, so I'll write this out. Okay, so von Mises is not just this rate. So if I'm going to sketch von Mises now, this area also is von Mises. Okay, Tresca is only the black line. Okay, von Mises is the red line covering everything including Tresca. So now to write this out, so if we were to, von Mises right, so von Mises is less conservative when compared to Tresca. Okay, so I'm going to label them at different points now. So this is your point A. I'm going to call at 45 degrees angle over here. I need to make sure it's 45 degrees. Right, so if I'm going to draw a 45 degrees, right, so this is close to 45. So this is my point C. This is my point B. And this is my point D. Right, so what we can say down here, if we look at based on von Mises, right, so based on von Mises, okay, so on the left hand side we have von Mises, and then on the right hand side we have Tresca. Okay, so we look at different points, point A, point B, point C, and point D. So at point A, right, when you look at point A, right, where you have stress A is equal to stress B and is equal to stress yield, right? Tresca is also stress A is equal to stress B the stress U. And at point B, you'll see that stress A is equal to stress B, and is equal to minus stress U. Okay, so stress A is also equal to stress B minus stress U. So this at point A and point B, they're the same, right? What is unique is at point C and point D is that minus stress A at point C is minus stress A is equal to stress B, right? And this will be equal to minus 0.557 stress U at point C. And then at Tresca, stress A is equal to minus stress B, and this is equal to 0.5 stress U. So 0.5 stress U is Tresca, but Vomisis happen to be what? 0.557. So likewise at point D, stress A is equal to minus stress B, and this is equal to 0.557 stress U. So likewise for this one, stress A is equal to minus stress B, and this is equal to 0.5 stress U. So this magnitude, right? This magnitude shows that Vomisis is less conservative. Okay, it's less conservative. So now the dying question is, how? Right? The dying question now is this: how do we get (0.577)? Okay, or why? Okay, how do we get 0.77 stress? Okay, so that condition where stress A is will be equal to stress B, okay, when stress A, right, will be equal to minus stress B, or stress B will be equal to minus stress A, will only occur in the pure shear condition. So what do I mean by pure shear condition? Okay, so let's say if we have our element now, so this is our X, this is our Y. So we were to draw okay. So under pure shear, we only have this condition. So this is our shear XY, right? And shear YX. And this is where we have our point X. And this is where we have a point Y. So when we sketch out mole circle, right? When we sketch out mole circle, we have this expression now. Or we have this, right? So this is normal stress. And then we have our shearing stress, right? And because stress X is equal to stress Y is equal to 0, we also know that this is our stress X and stress Y line, right? And then we have our shear. So for example, this is our shear. Okay, so this is our shear line, right? And the next one down here, this is our shear line. And point X, the element is going anti-clockwise. So over here, this is a point X. And over here, this is your point what? Y, going clockwise. So now you construct your mole circle. So at this stage, you realize for your mole circle, over here, this is your stress A. Right, your principal stress. And this circle over here is your what? Stress B. Okay, so this is where we have a pure shear, and then once we know that only under pure shear condition this apply, right? So we can state that when stress A is equal to minus stress B, right? and substitute into von Mises equation, right? So what we have is stress A squared, right, minus stress A, stress B, plus by stress B squared, and we include the yield criteria at stress Y squared. Okay, so when we substitute, we're going to substitute, okay, we're going to substitute this stress A minus stress is equal to minus stress. So you have stress A squared minus stress A, or plus by stress A squared, minus minus plus, plus by stress A squared. This is called stress U squared. So what you have is 3 stress A squared is equal to stress Y squared. So let me, if you forget, stress capital Y is a U stress, and stress A and B are the what? Principal stresses. Okay, so over here you have stress A is equal to stress U plus by minus divide by square root 3. So this will be equal to 0.577 stress U. Okay, so we know for Tresca, so this is von Mises, right? So for Tresca, okay, so for Tresca, we know that the condition is stress A and stress B must be equal to half of your stress U. Okay, so that's how we get 0.577. Okay, well, Tresca declare that the shear stress, right? Your shear stress is half. Maximum shear stress is half of its what? Of its U. Okay, so that's the difference between these two criteria. They are very commonly used for ductile material. Okay, I'll come back for another example.